At 760 millimeters of mercury, we also called that torr, the normal boiling point for water is 100 degrees Celsius. This intersection right here. The normal boiling point of ethanol at 500 millimeter mercury, or that word torr, is 68.1 degrees. And it's the intersection right about here. So what we're looking at, the effects of temperature versus vapor pressure. Where does a solution boil? Boiling, of course, is truly defined as when we're in dynamic equilibrium with the vapor pressure and the liquid phase, the solution will boil. If I raise the temperature, the boiling point is going to follow. Raise the pressure, same thing will happen. So pressure affects the temperature of the vapor pressure. This is hard to look at without the color coding. I know in the colored PowerPoint, these were all color-coded lines. Which of the following is the most volatile? The word volatile means which is the least attracted to each other. What would be the non-polar molecule? What would be the easiest to escape from the liquid to the gaseous phase? If I think of just the structures, here's water, HOH, very polar. Titanium tetrachloride, non-polar. Ether has the oxygen in the middle. Whoops, that's a carbon. Non-polar. Ethanol, this OH group at the end, very polar. Acetone, very polar. What's hard to detect is what line is representing, because these are all color-coded in the graph. So not relying too much on the color coding here, the most non-polar molecule has the least intermolecular attractions, therefore would be the most volatile. Volatile, who's escaping from the liquid to the gaseous phase at the highest rate? Who's existing in the gas phase the most? Well, it's the one with the least attraction to each other, which would be the non-polar molecule. Which of the following has the strongest intermolecular attractions? So therefore we're looking at which one has the lowest vapor pressure. And the lowest vapor pressure would come from a molecule that has very strong intermolecular attractions. Not only do they have dipole-dipole, but they'd also have hydrogen bonding. A water molecule. Water molecule has a very high boiling point. Ethanol might be another one what I would consider to have very strong intermolecular attractions, because ethanol, recall we just drew that, also could have the hydrogen bonding. So here we have a water molecule that can exhibit hydrogen bonding and is polar. The ethanol exhibits hydrogen bonding and is polar, and very strong intermolecular attractions. They are very non-volatile. Water, of course, with that bent geometry, would have the strongest intermolecular attractions, being a liquid with a very high boiling point. Ethanol's boiling point, about 89 degrees. So the very term boiling point, when a temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, we're going to start seeing it bubble. And not just at a surface, but a full rumble. That phenomenon is what we call boiling, and a temperature at which the vapor pressure equals the external pressure, which is atmospheric pressure, is known as the boiling point. The term normal boiling point is at standard pressure, 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals. And they're just showing us that elevation affects the boiling point. So the higher we are, the thinner the air, the lower the pressure, the lower the boiling point. All the way to sea level in Boston, Massachusetts, where water would boil at 100. Keep climbing up in elevation where air thins out and pressure drops, At the top of Mount Everest, our water would boil about 78 degrees Celsius. So when the vapor pressure lowers, the atmospheric pressure lowers, the boiling point is actually lower. I know even when you're cooking, there are sometimes high altitude directions if you're cooking or baking a cake where you're looking at elevation in terms of how long you should bake the cake, how much flour, how much baking soda you should put in to increase the carbon dioxide expansion. So boiling points are called when vapor pressure and the external pressure of the air are indeed equal. Yep, this is next. Which of the following has the highest normal boiling point? The term normal is just 760 millimeters of mercury. 760 millimeters of mercury, the highest boiling point is the compound, and again, they're not well marked to tell you which one it is. I can't just based on the graph. I'm not sure which one it would be. But over here, that's how we would read that. I could get out the color-coded, and we'll discuss that in class. I'll pull out these color-coded slides, and we can take a look. Whatever color-coded line this is the highest temperature that I'm reading across at the normal, which is just standard pressure, 760. The term critical point. This term is described as the temperature required to produce a supercritical fluid. Supercritical just simply means, down here, at the pressure, the critical temperature is called the critical pressure. At the critical temperature or higher, the gas cannot be condensed to a liquid, no matter how high the pressure gets. The term critical point, where I can no longer distinguish between the liquid and gaseous phase. And it's easy to see that perhaps on a graph instead, and I'm just going to draw one over here. If this is atmosphere and pressure, atmospheric pressure is increasing up the y-axis, and this is temperature, which is increasing along the x-axis. We have an equilibrium, typically along this line, where we have at very low temperatures the solid phase. In between temperatures, we would have the liquid phase, and at high pressure, high temperature, we'd have what's called the gaseous phase. Sometimes they have more of every substance has a unique looking triple point graph. So it could be kind of a flatter slope here, sometimes it's a higher slope, but it shows all three phases, where all three phases are in equilibrium together, is a point on our graph. But this term up here, where the liquid phase and the gaseous phase, there's a definite end to where I can no longer distinguish the two phases when the pressure and the temperature gets high. So at that critical temperature or higher, you can't tell them apart anymore. So high pressure, high temperature, and we reach what's called a critical point. You can't distinguish the liquid and the gaseous phase. The next topic is sublimation and deposition. This is a phase change when a solid goes directly to the gas, or a gas goes directly back to a solid, skipping the liquid phase. Dry ice